Hi everyone, and welcome back to another physics lesson. I'm so glad to have you here with me today. Today's topic is on color mixing, and we'll be talking about color mixing with regard to pigment and light. Before we get into it, it is time for the most important question of this video, which is, who's excited for physics? Again, so happy that you're here tuning in and learning about colors, which is a really cool topic. So the main question that we'll be addressing in this video is, how do we see and perceive color? How do we do that? Before we get into that, let's talk about how light can interact with matter. And so it can be reflected off of matter, it can be absorbed by matter, and it can also be transmitted through matter. So remember that reflection, as you can see in this image, is when light bounces off of the object. Absorption is when the light is absorbed by that object, and the energy is then also absorbed by the object, usually in the form of heat. And then transmission is when light passes through the object. And based off of what colors are reflected, absorbed, or transmitted through an object, that will dictate or determine what colors we see in that object. So let's start with this example here of a yellow daffodil and talk about how it gets the yellow and green colors that it has. First, we know that white light, just like the light all around us, it's coming from the sun, includes all the wavelengths of light. And white light is hitting this flower, but the flower petals are only reflecting certain wavelengths of light that correspond to yellow light, meaning that the light that is reflected off that flower is yellow light. It has the wavelength corresponding to yellow light. All the other colors of the rainbow are absorbed by the flower. Likewise, the stem appears to be green to us because that stem is reflecting the wavelength that belongs to green light and absorbing all the other colors. In other words, one way to describe how we see colors that we do is that the wavelengths that are reflected or absorbed dictate what we actually see. We see the color of the wavelengths or wavelength that is or are reflected. So if an object is purple, it is reflecting purple light and absorbing everything else. If an object is red, it is reflecting red light and absorbing everything else. Remember that colors can be broken down by different wavelengths, with violet having the shortest wavelength and then therefore the highest frequency, and red having the longest wavelength and therefore the lowest frequency. But what about white light or black light? White light is when all of the wavelengths of light are hitting an object and reflect off the object, while black light is when all the wavelengths of light hit the object are instead absorbed by the object. So none of that light is reflected back. Let's talk about cars in the sun. So based off of the fact that white light reflects all light energy and black absorbs all light energy, which car would you rather touch when it is parked in the sun? I think we've all made the mistake of touching a black car in the heat and it gets really hot. You scream and you move your hand away, or maybe you don't scream, you just move your hand away. But black cars in the sun are so hot, pretty sure you avoid touching them at all costs. And that is because black cars absorb all wavelengths of light and therefore are getting really hot. They're absorbing all of that heat energy, while the white cars are reflecting that light back out. Therefore, I would much rather touch a white car in the heat. But what about looking at a car? I think we've also been blinded by really bright white cars in the sun. I mean, it even hurts my eyes to look at a piece of paper in direct sunlight. And that is because the color white is reflecting all wavelengths of light back into our eyes, while black is absorbing that light. Therefore, I'd much rather look at a black car in the sun because it is much easier on my eyes. So now that we know what wavelengths of light correspond to what colors, how do we actually detect these wavelengths? Well, it goes back to the types of cells that are located in our eyes. And there are two types of light-sensitive cells in our eyes, known as rods and cones. Rods have to do with how light or dark an object is, whereas cones are color receptors. Light will either activate a red cone, a green cone, or a blue cone. Therefore, we have 3 cones in our eyes, each of them detecting a range of specific wavelengths sensitive to red, green, and blue. So how do our brains interpret color? Well, if one of our cones is activated, then we simply see that color. So for example, if we see a wavelength of 575 nanometers, we are activating our red cone and we see red. But clearly we don't only see red, green, and blue in the world. So how do we see colors that fall in between these wavelengths on the spectrum? Let's talk about the color yellow because we don't have a yellow cone. And also that color yellow was in our daffodil from before. Well, our brains have developed the ability to interpret yellow if it sees that yellow wavelength, but it can also see yellow if it gets a combination of red and green wavelengths that are both firing at the same time. If our red and green cone receptors are being activated, that will actually help us get yellow, which is a color right in between green and red. So there are several ways that humans can perceive color, whether or not the true wavelength of that color is present. And this is where color mixing comes in. So there are two ways to mix colors. You can talk about mixing light, which has to do with color addition, and we'll talk about why it's called that. Or you can talk about mixing pigments or paints, which is also involved with color subtraction. And again, we'll discuss how they're different and how they involve addition or subtraction of colors. Let's go ahead and start with mixing light, since we just talked about wavelengths of light and the cones in our eyes, how that light is reflected or absorbed. Some sources of light can be stage lights, or the classic example of the sun. Now, the primary colors of light are red, green, and blue, which matches with the colors that are recognized by the cone cells in our eyes. The secondary colors are combinations of these three primary colors. In other words, when you add light to each other, you get the other colors. This gives mixing light the name of color addition. For example, when you mix red and green, you get yellow. When you mix red and blue, you get magenta, and when you mix green and blue, you get cyan. Complementary colors are what colors are directly opposite of each other on this color wheel. So as you can see, red and cyan are complementary, green and magenta are complementary, and blue and yellow are complementary. These are the complementary colors. Again, they're opposite each other on this color wheel. Now, how do we get white light? Well, we mentioned this before. To create white light, we no longer need every single wavelength, but we just need to combine red, green, and blue light, because those are the three primary colors, and that basically captures every single color in between. However, to get white light, we can also do this. We can also combine the secondary colors, magenta, cyan, and yellow, to each other. Why does this work? Well, combining these secondary colors is essentially combining the primary colors because they are composed of the primary colors. Let's take a look over here. Even if you just combine yellow and magenta, you will inherently have red and green from yellow and red and blue from magenta, and you will therefore have red, green, and blue in just yellow and magenta, and therefore that will create white. The same can be said for magenta and cyan and yellow. So color addition works a lot with TVs. Our TVs rely heavily on producing red, green, and blue light at different levels of intensity, and they can combine these three colors to make basically any color on the spectrum by varying how much of each color is present in each pixel on your television. To some, mixing light is known as color addition because it asks the following question: what colors do I get when I add different colors together? Now let's go ahead and move on to mixing pigments. This might be more familiar to you, especially if growing up you took an art class. In that class, you may have learned about primary and secondary colors of paint. I remember learning about the primary colors of paint as red, blue, and yellow, but technically the primary colors of paint are magenta, not red, cyan, not blue, and yellow. How pigments work is by absorbing one color of light, which happens to be the complementary color of that pigment. Then every other light that is not absorbed is combined to give you the color that is then reflected. So for example, let's say you want to paint something that was cyan. That means that something is absorbing its complementary light, which is red light. Okay, so you want to paint cyan, and the complementary light would be red. What light is being reflected would be the green and blue light, which would combine to give you cyan. Let's use a graphic to show us how this happens. Remember that the primary light colors are red, green, and blue. And when we have white light, it is a combination of all three of these colors together. Also remember that primary pigments absorb one of these primary light colors and therefore reflect the other two that are remaining. The two reflected lights then combine to give us the primary pigment colors that we see. In other words, what is happening is that you are subtracting the one primary light that is being absorbed by the pigment and leaving the two primary lights left to combine and give you another color. Let's apply this to the example of yellow. Yellow pigment absorbs its complementary color, which is blue, and therefore the blue is subtracted from the white light, leaving red and green light. What is reflected off this pigment then is red and green, and as you can see from this color wheel, red and green combine to give us yellow, and that's why we see yellow light when blue pigment is absorbed. What about magenta? Magenta pigment absorbs or subtracts green light, as you can see right here, okay? And so what is left would be red and blue light. And if you can take a look at this color wheel, red and blue light combine to give us magenta. And so we'll see magenta light or magenta color when green is absorbed. The same pattern can be said for cyan, which we talked about before. Cyan absorbs or subtracts its complementary color, which is red. And then what is reflected are its remaining primary colors of green and blue. And green and blue combined give us cyan. So what happens when we combine pigments together? These three primary pigments can be combined to give us three secondary colors of paint, which are red, green, and blue. This color wheel shows us examples of how these primary pigments can be combined to give us secondary colors. Cyan and magenta give us blue, magenta and yellow give us red, and yellow and cyan give us green. If you notice, the primary secondary colors of light and pigment are flip-flopped, such that the primary colors of light are the secondary colors of pigment, and the secondary colors of light are the primary colors of pigment. Why does this happen? Again, this has to do with color subtraction. Remember that the primary light colors that comprise white light are red, green, and blue, and each primary pigment absorbs one of these lights. When we then mix two pigments together, we're now subtracting two colors from the white light. Then whatever primary light color is left of red, green, or blue will be the light that is reflected. Let's start with the first example of combining yellow and magenta. Yellow absorbs its complementary color of blue, as you can see. Once we pass through yellow, blue no longer exists, while magenta absorbs its complementary color of green. As you can see, past magenta, green is no longer there. So the only color that is reflected would be red. Therefore, yellow and magenta can combine to give us red. What about adding yellow and cyan? Again, yellow absorbs its complementary color of blue, so beyond yellow, blue is no longer reflected, while cyan absorbs its complementary color of red. Therefore, beyond cyan, red is no longer reflected. The only color that is left is green, and green is reflected, and so yellow and cyan gives us green. This same pattern applies for magenta. So to sum, mixing pigments has to do with color subtraction, which asks the question, what colors are left when I subtract them from each other? Let's go back to our original example of the daffodil. This idea of color mixing changes a little bit of what we initially explained about the colors of this daffodil. It no longer needs to only reflect yellow. If we wanted to produce this image with a TV screen, for example, the pixels that are representing the daffodil can reflect red and green light, which combine to give us yellow. Or if you were painting this daffodil, then your pigment would have to absorb blue light, because remember, pigments or paints absorb the complementary color of the pigment, and yellow's complementary color is blue, as you can see right here. Yellow and blue are complementary of each other. Let's talk about the stem. The stem of this daffodil is green, which means that it must be reflecting green light and absorbing blue and red light, or magenta light if blue and red are combined. So I want you to now pause this video and practice filling out this chart by identifying what light, red, green, or blue, needs to be reflected, absorbed, or will be painted based on this color wheel. Pause this video and see if you can figure it out. So let's go ahead and review this table. The first thing I want you to notice is the setup of the color wheel. Just to remind you, red, blue, and green are our primary colors of light, while magenta, yellow, and cyan are the primary colors of pigment. These will impact what colors are available to be reflected, absorbed, or painted with. Now let's go through examples starting with the top left. Let's say that we have yellow paint. To get the color yellow, we need to absorb its complementary color, which is blue, right? So to get the color yellow, we will be absorbing one light. In this case, it would be blue, because it's complementary of yellow. What is then reflected off of this yellow paint are the remaining light colors, red and green. And when we combine red and green together, that gives us yellow. Let's do another paint example. Let's say that we want the color to be magenta. That means that the pigment must be absorbing its complementary color, and so its complementary color is green. Therefore, the paint that we're painting with will be reflecting the two remaining colors, which are red and blue, and if we combine red and blue, that gives us magenta. Let's move on to light reflection now. If we want the color green to be reflected, then the other primary light colors would be absorbed, which are blue and red. The color you would paint with to achieve green would be yellow and cyan, because these are the pigments that absorb blue and red light. Yellow absorbs blue, and cyan absorbs red. Therefore, the only light that is not absorbed by the pigment would be green, and green would be reflected. Finally, if we want blue light to be reflected, then the other primary colors would be absorbed. Okay, so that means that we would be absorbing red and green light. How do we absorb this red and green light? Well, we absorb them with pigments, and the pigments that absorb red and green light are their complementary colors. So red would be absorbed by the color cyan, and green would be absorbed by the color magenta. So that means you would have to paint with the colors cyan and magenta that would absorb red and green light, leaving the only light that is not absorbed to be blue. Now, I know this is a very tricky and complicated concept, and I don't expect you to memorize a color wheel or to know all of these combinations. What I do want you to know is that there's more than one way to achieve a certain color, and that what we see, for example, on the TV is a result of varying levels of red, green, and blue light, which correspond to the light detecting cones in our eyes. As always, thank you so much for watching this video and tuning in. I hope you learned something new. Always remember, this is fine, and I can do it. Thank you guys. I'll see you in the next video.